Welcome, everybody, to this week's edition of the Center for Data and Computing Distinguished Speaker Series. Our speaker today is journalist and author Brian Christian, and I will turn it over now to CDAC Director Nick Feemster to do a brief introduction.
Thanks, everyone. Welcome to today's Distinguished Speaker Series. And for today's speaker, I'm very, very delighted to introduce Brian Christian. Brian is the author of several New York Times bestsellers, including The Most Human, which is a book about sort of what it means to be alive, and can computers think? And most recently, also he has he's got another book called Algorithms to Live By, which is sort of coupling computer science with human decision making. With his colleague and associate Tom Griffiths, who's on the faculty at many of you may know Tom. He's on the computer science faculty now at Princeton, and most recently and I think we'll hear about today. He has published another book called The Alignment Problem, and this is, I think, the topic of today's discussion, which is really what happens when we build AI systems and they don't necessarily align with our values, and what to do about it. And so I'm excited for the talk today. This looks just totally interesting and fascinating. And Brian, it's great to have you. And we look forward to the talk. Thank you.
Thank you so much, Nick. And it's really my pleasure to be here. All the more so because of how central a role Chicago, and in particular the University of Chicago, ends up playing, both to the history of this field and to the work that's happening at the present. So I believe, as I suspect many of you do as well, that the field of machine learning has come in the last 5 years or so to a kind of critical crossroads. But actually, I believe that this story really begins in 1938 at the University of Chicago. And it is in 1938 that Bertrand Russell has arrived at the University of Chicago to give a series of lectures. And the news of this makes its way to a young teenager in Detroit by the name of Walter Pitts. This is a later photo of Pitts, but Pitts runs away from home at the age of 15 and comes to Chicago to attend Russell's lectures, and ends up living essentially as a homeless teenager in Chicago, dropping in on professors' office hours. And it is there in 1941 that he meets Warren McCulloch, who has just arrived from Yale as part of the neurology faculty at University of Illinois, Chicago. And the two of them begin this kind of lifelong collaboration, which is this intergenerational friendship in which Warren McCulloch also becomes kind of Walter Pitts' foster father. And he invites Pitts to come live with him in the basement of his family's house in Hinsdale, Illinois, a suburb out on the west outskirts of Chicago. And this family home, in which Pitts becomes a kind of adopted son, is this legendary space of intellectual activity and artistic activity as well. A lot of these guys were writing poetry, and I think that's kind of an underappreciated footnote in the history of machine learning. And one of my prized possessions, I don't know if you can see it here, is a copy of McCulloch's book of poems called The Natural Fit, which was published by the Chicago Literary Club. But it is through this collaboration and this really unlikely and beautiful friendship between Pitts, the teenage prodigy logician, and Warren McCulloch, this mid-career esteemed neurologist, that we really have the birth of this idea of thinking about the brain mathematically and logically, and what might be possible to do with this artificial mathematical version of the human brain. And of course, I don't have to tell you the long storied history of neural networks over the 20th century with many excitements and roadblocks along the way. But I think just to distill, where we find ourselves at the moment into a single image or a single chart, for me, it is really the 2012 ImageNet competition that marks the turning point and really the birth of deep learning. And we can see over this 8-year period, the error rate in image recognition goes down by something like 90% in less than a decade. And we now find ourselves at a moment where this sort of technology is getting ubiquitously deployed, and in fact, often invisibly. We now, in the 2020s, if you have a modern iPhone or Android phone, you can't even take a photograph without, in this case, in the case of the iPhone, an 11 to 12 stage ML pipeline running in the background that's calculating the focal length, the focus, et cetera, compositing multiple exposures, et cetera, all based on what it thinks it's seeing and what it thinks it's seeing ought to look like. At the same time, we have this trend, this incredible acceleration in the field of ML, intersecting with a second trend, which I think is less celebrated, but just as significant, which is the permeation of statistical and machine learning methods into the, I would say, decision-making infrastructure of society. So this is a chart that was made by then UC Chicago law professor Bernard Harcourt and his student Marilyn Hunt-Dorda, looking at the evolution of parole prediction instruments used in US states. And this has a surprisingly long history. We'll talk a little bit about that deep history later, but you can see just this totally exponential adoption at the end of the 20th century. We now find ourselves in a moment where these sorts of formal models are so ubiquitous that Chief Justice, U.S. Supreme Court Chief Justice John Roberts can visit Rensselaer Polytechnic Institute, and when he's asked by University President Shirley Ann Jackson, can you foresee a day when artificial intelligence will assist with courtroom fact-finding or even more controversially judicial decision-making? He replies without hesitating, yes, that day is already here. That day has already come. And so I think it is really through the intersection of these two trends that people began, as we know, to get concerned. Now, these concerns are hardly themselves new. In fact, they go back almost as far as the field of machine learning itself. And I'm thinking here of MIT cyberneticist Norbert Wiener, who has this famous 1960 essay, The Moral and Technical Consequences of Automation, where he has, I think, this very seminal paragraph. We all know the fable of the sorcerer's apprentice, in which the boy makes the broom carry water in his master's absence, so that it's on the point of drowning him when the master reappears. Some people know this as the Goethe poem. Most of us, I think, know it as the lovable 1930s cartoon with Mickey Mouse, where he animates this broom, but things go horribly wrong. And by the end, he's, practically drowning, trying to figure out how he can undo the spell that he's cast. And Wiener writes, disastrous results like this are to be expected, not merely in the world of fairy tales, but in the real world. If we use to achieve our purposes a mechanical agency with whose operation we cannot efficiently interfere once we've started it, then we had better be quite sure that the purpose put into the machine is the purpose which we really desire, and not merely a colorful imitation of it. And as I say, this concern goes back to the early 60s, but it is really now, I think, that this has become an acute and urgent problem for the field. And it now has a new name, which is the alignment problem. This question of whether our machine learning systems are really learning the things we're learning, and whether, more pointedly, they are going to behave the way we expect them and intend for them to behave. So I began around the summer of 2016 to sense that there was really something happening in the field, and that we were witnessing, I would say, the birth of a certainly a movement, if not an entire field, at the kind of interdisciplinary intersection of these questions of ethics and safety in machine learning. And so I set out on what would ultimately be, I guess, a four-year research quest to get to the bottom of that story historically, and to talk to as many people as I could, and to tell it as much as a curriculum as a story of how we got here and where we are. The rapid progress, the sort of coming together of this interdisciplinary community, the rapid progress made in, I think, a pretty breathtakingly short period of time, but also the frontier of open problems that remain. And the book ends up telling about 100 different stories through these profiles of individual researchers. So, of course, given our time, we can only scratch the surface, but I want to highlight a few of those and take us through some of what I see as kind of the key progress that we've made and key open problems that linger at the frontier of this field. So broadly, when we think about a machine learning system, we think of it as having training data and an objective function. This set of examples and this way of measuring, or articulating, formalizing what we want the system to do. So I think that's a useful way to kind of break down a taxonomy of how to approach this. So we'll start with the training data, which I think is a reasonable place to start. Now, I think many of us in the audience are familiar with some of these kind of signature catastrophes in, image recognition. For example, in 2015, the software developer Jackie Alcine logs onto Google Photos and finds that they've deployed this new convolutional neural network that is automatically grouping your photos into albums and giving each one a descriptive caption. And he discovers, to his horror, that Google Photos has put together an album of selfies of himself and his friend and given it the caption "gorillas." And I think this was, for many people, both in the industry and in the academy, really a kind of wake-up call. And we've seen a lot of work in the wake of incidents like this on trying to get to the bottom of what's going on in the training data, what's going on in these kind of disparity in accuracy rates. And I think of MIT's Joy Buolamwini and Timnit Gebru, who you are going to have the privilege of hearing from in just a couple weeks as part of the speaker series. So I won't say perhaps too much about her work because she'll get to tell you about it herself. But I think they've done together some really foundational intersectional analysis of facial recognition, face identification, classification systems, showing both the kind of incredibly wide disparity in accuracy rates, as well as offering data sets like their parliamentary data set, which is organized by Fitzpatrick skin type, which offers a set of diagnostic tools and a way to think about some of these commercial systems. And we've seen the impact of that work already. I think it's very amazing to just point out the sea change in the way that the industry is thinking about these data sets. And for me, there's no better illustration of this than the labeled Faces in the Wild data set, which came out in 2007. And if you look at the research paper that accompanied it, it says, the set clearly has its own biases. However, the diversity of pictures present is very large. But what they're talking about is the lighting and the angle of the face. And I don't think anyone in 2021 would talk about the bias or diversity of a facial recognition data set and mean lighting, right? And indeed, we've seen just as recently as the late 2019, Label Faces in the Wild now comes with this giant red disclaimer that says many groups of people are not well represented in the way that we talk about these data sets and the questions that we're asking when we put them together. This is an issue that, what goes into these data sets, what they end up containing, is an issue not just for thinking about the ethical impacts, but also for thinking about, physical safety. So this is Tesla head of AI, Andrej Karpathy, And I'm stealing a slide from one of his presentations. He's talking about his lost sleep. As a PhD student, 95% of his lost sleep was models and algorithms. And today, as director of AI at Tesla, 75% of his lost sleep is data sets. And I think that's appropriate, and perhaps unfortunately so. If you look at the kind of history of these early self-driving car accidents, for example, the self-driving Uber that killed the pedestrian in Tempe, Arizona in 2018, one of the contributing factors to the crash was the fact that the training data appeared only to contain pictures of people crossing the street at crosswalks. And so the system was just kind of fundamentally ontologically unprepared to encounter a person jaywalking, because it had never seen an example of a jaywalker. So these questions of, does the data set really represent the world in which it's going to be deployed, have ramifications at many, many different areas of machine learning. And there's a question, once we train a model, in many cases, we don't, especially as researchers, we don't necessarily have access to the actual data set that the model was trained on. We just have the final model. And so are there things that we can do diagnostically to figure out if something might be wrong before we actually deploy it? And there's a lot of, I think, really exhilarating work here in the space of transparency. People like Chris Olah, who leads the Clarity team at OpenAI, has done this work on kind of using classifiers in a generative mode, where you present them with essentially static, and then you fine-tune the static to maximize the output of a particular category label. And you can use this as a kind of sanity check. Are the categories that this model has learned, do they pass the smell test? Do they seem like what we expect? In this case, anemone fish, banana, parachute, screw looks basically right. But then you look at something like dumbbell, and you see, for example, that dumbbells come with this weird disembodied arm just flexing into outer space. And I think this is a really useful moment from a kind of bias diversity of data set perspective, which is to say, the model has learned that dumbbells are often found at the end of flexing muscular arms, which is certainly true. However, this implies that the model is not reliable at identifying a dumbbell that's on the ground or on a rack or something like that. So it is precisely this sort of thing that can indicate where the gaps in the training data might be. Another person who I think has contributed a lot of really foundational work here is Bean Kim from Google Brain. And she has a method called testing with concept activation vectors, or TCAV, that uses the internal activations of a network to suggest the importance of certain high-level concepts to a model's final classification. And again, this offers us kind of a sanity check. So if a zebra has, stripes are important, a horse-like appearance is important, a savanna is important, maybe that seems normal. For a doctor, if a white lab coat and a stethoscope are important, but so is being male, then we might have an indication that something is going on in our data set. And as you've heard a few weeks ago, Olga Rusikovsky has done a lot of really good work in terms of figuring out how you mitigate those issues. And so I think techniques like this go really hand in hand. And sometimes they can be incredibly subtle. So Bean Kim looked at the Inception v3 model that Google was using at the time, and it showed that fire trucks, for example, classifying something as a fire truck is very intimately related to the object being red. Well, this makes a fair amount of sense from a US context, where fire trucks are almost always red. In the UK, they're typically red as well, but in Australia, they are often white, or in Canberra, they're neon yellow. And so again, this suggests to us that there might be a discrepancy between kind of the distribution of images that we've trained the model on and what it might actually see if we deploy it, for example, in Australia in production. So this is, again, something that we I think cuts across what we typically think of as the kind of ethics community and the safety community. So this is Dario Amodei, who has for many years led the safety team at OpenAI. And one of the canonical AI safety problems, going back to the concrete problems in AI safety paper from 2016, is what we call robustness to distributional shift, or robustness to distributional change. And I think about this as being maybe sort of a last line of defense in cases like this, where even if there is some problem in the data set where there are insufficient examples of a certain type of thing, and even if our transparency methods are insufficient to identify that, what we might want as kind of a final fail-safe is that the model itself can realize that it's operating out of its comfort zone, so to speak, and have some way to quantify essentially its own uncertainty or the fact that it's kind of out of its distribution, and take some action to, perhaps turn itself off or defer to a human, or, make an alert, whatever it might be. And we're seeing a lot of really interesting work here. So University of Oregon's Tom Dietrich has done a lot of work on this notion of open category learning. So, implicitly, when you train an image classifier, you give it this kind of pre-built ontology of these are the 1,000 categories that anything can be in, and it has to typically be in exactly one of those categories. And we assume it is, both mutually exclusive and exhaustive. But this is, of course, almost never the case. Many of the possible pixel combinations you could show a model do not belong to any of those categories. So how do you do this sort of open category learning? I think that's really, really important in this area. I'm also thinking about people like Oxford's Yaron Gall and Cambridge's Zubin Garamani, who have used dropout, shown that you can use dropout to approximate Bayesian inference and get a kind of calibrated measure of the model's uncertainty. And again, DeepMind's Victoria Krakovna has done work on trying to formalize the impact that an agent's action will take. And I think these two approaches dovetail really well together. That if you are going to take a very high impact and irreversible action, then you should set a higher bar for how certain the model has to be. And so we're seeing this kind of making its way now into robotics, where people like Berkeley's Gregory Kahn are using dropout uncertainty as a impact regularizer. If the collision model starts to become uncertain, the robot will slow down. And you can also imagine something like this in the Uber self-driving car scenario might have saved the woman's life, because she was walking a bicycle across the street, and the model had this ontology of either someone is a pedestrian or a cyclist. And it saw the bike and it thought, okay, she's a cyclist, but she's not on the bike. She appears to be walking. Is she a pedestrian? And it kept flickering basically back and forth many tens of times a second between these two category labels. And you would hope, I think, in this situation for something closer to what a human would experience, which is knowing that you don't know and sort of preemptively slowing down simply by virtue of your uncertainty itself. So we are starting to see methods like that coming into actual practice, which I think is a very encouraging sign. Okay, so that's the training data. Now, what about the objective function, right? That's the other side of the equation. How do we try to operationalize what it is that we want these models or these systems or these agents to actually do? Well, this turns out to be, as I'm sure many of you know, much trickier, much subtler, much deeper of a problem than it might seem on its surface. I think a perfect example of that is the criminal justice setting. So statistical methods for things like predicting reoffense in parole, in pretrial detention, have at this point almost a 100-year-long history. I think they really began in the year 1928 with the University of Chicago sociologist Ernest Burgess. And there's this wonderful sort of backstory that I tell in the book where he is appointed by Hinton Clabaugh, who is the head of the parole board in Illinois, who is very, shall we say, skeptical that parole is even a good idea in the first place. He says, the pendulum of justice and mercy has swung to the extreme in favor of criminals. And he's not sure that ever releasing someone early is ever a good idea. And he assigns Ernest Burgess to prepare a report for him on whether or not you can predict the success of releasing someone early on parole. And the result is this 1928 book, which is another prized possession of mine, that ends up getting sent to the parole board and completely changes his mind. So Burgess writes, there can be no doubt of the feasibility of determining the factors governing the success or failure of the man on parole. And this changes Clabaugh's mind. And as he writes in the foreword of the book, my first impression was that indeterminate sentences and parole laws were an asset to criminals. Proof to the contrary is overwhelming, and I now believe these laws, properly administered, to be decidedly beneficial to society as well as to the individual. And so this is really the beginning of modern, what we would now call risk assessment. And this gets into practice. In state of Illinois is the first state to use it in 1935. And as we saw in that graph, there was sort of an exponential adoption that followed. But telling this story from the 21st century perspective is a little bit more complicated because we've seen that it can be very, very tricky indeed to make sure that these models are having what feels to us to be a fair impact or are used in a way that's equitable. And so I think, again, this will be familiar to many people in the audience, but Julia Angwin at ProPublica and her collaborators have done some very, very influential work in this area in 2016 on the COMPAS tool, which is one of the most widely used tools in the US, suggesting that there are these very troubling disparities in the error rates in particular, as far as they affect Black versus white defendants. And part of what was fascinating to me as I interviewed people, both Angwin herself and many computer scientists, was the way that this article in particular kind of galvanized and kicked off an entire kind of subculture within the machine learning, within the statistics community. And so I'm thinking about people like Moritz Hart from Berkeley, Eric Price from UT Austin, and Nadi Srebro from University of Chicago, who have done some work formalizing these different kind of ethical desiderata. For example, you have calibration by group, which has been kind of the gold standard used by criminologists for many decades, which says, if you're given an 8 out of 10 risk, then you should be rearrested at the same rate, on average, as someone else who's given an 8 out of 10 risk, regardless of your racial group. That seems like the kind of thing we would want a fair model to do. But there are other ways of operationalizing what fairness might mean. For example, they talk about things like equalized odds or equality of opportunity, where you start to look at the error rates, the false negatives and false positives, and ask whether the kind of proportion of the errors, the types of errors the model is making, hold similarly from one group to another. And it's famously on this measure that the COMPAS tool fails. And so having now articulated these different ways of actually operationalizing what fairness might mean in a classifier, we can ask this, I think, obvious question of, well, can't we just have all of those things? And the answer is essentially no. So there's some really foundational work here from John Kleinberg at Cornell, Sendhil Mullainathan of University of Chicago, and Manish Raghavan, also of Cornell, and along with a number of kind of concurrent papers by Alex Choldachova at Carnegie Mellon, Sam Corbett Davies, and others at Stanford, essentially showing no, you simply mathematically you cannot satisfy these different constraints at the same time. And so that, I think, is that really is the beginning of a policy conversation of what are the possible trade-offs I think it's really at the boundary between computer science and policy. We can explore the space of trade-offs, but then ultimately I think it's a policy choice in terms of what we want to prioritize. And so we're seeing, I think, really just the very beginning of this conversation between these two fields, and one that I think is very, very impactful. But in some ways, I think there are even bigger questions that we can ask about a tool like Compass in terms of whether the tool is really doing what we want. And so we can zoom out from the actual, the constraint that we put on the model to these, I think, bigger questions. And the first is, what are we really measuring in the first place? So often people talk in a kind of shorthand way about measuring or predicting recidivism or reoffense. It's very critical to highlight that that's not something that we can actually measure. We can only measure rearrest and reconviction. Now, this was something that came up as I was doing some archival research here. And I was looking at old copies of the Chicago Tribune from the 1930s. I was curious, what was the public discourse like around the time that the first generation of statistical risk assessment models went into practice? And I was surprised to find the following article by Elmer Schnackenberg, who was, I think, the minority leader of the Republican Party in the Illinois State House at the time. And he's complaining, quote, because a parolee isn't caught at crime during the first or second years of his parole, he is listed during those 2 years as having made good. And I think this is very interesting because he's pointing to this gap between what we can measure and what we're really trying to predict. And so he's saying, now wait a minute, just because we have some criminal mastermind committing all these crimes and not getting caught, not only is he still out in public, but our model is going to kind of interpret this as a data point of, someone who was reformed, and we're going to recommend releasing other people that fit that similar, profile. That doesn't seem right. And I think this is really interesting because from a contemporary perspective, you hear the same criticism, but it's being made the other direction, right? Being made by progressives saying, now, wait a minute, just because someone is wrongfully arrested and wrongfully convicted, not only is there an injustice to that person, but they're getting tagged, the sort of ground truth, quote unquote, is getting tagged into this model as this person recidivated, and the model is going to recommend detaining more people like that. And so to me, it's just a historical, there's something historically interesting that the political valence of the critique has flipped in the last century, but it's really the same critique, which is that we're not actually measuring the thing that we're trying to predict. And this, there are many, many ways that this sort of gap can creep into machine learning systems. We see it even in the ImageNet competition. So this is, again, Andrej Karpathy, who now runs AI at Tesla, but in his graduate student days, he was himself the human guinea pig for the ImageNet competition. He was the human baseline, so to speak. He spent 2 weeks painstakingly training himself to identify, different dog breeds and different species of birds and things like this. And at the end of that 2 weeks, was able to get himself up to a 95% accuracy on ImageNet. But you might say 95% accuracy with respect to what? Well, not truth, consensus. You can see even in this figure from the original AlexNet paper, some of the quote unquote errors that the model makes. It thinks that a grill is actually a convertible, or it thinks that a cherry is actually a Dalmatian. But looking at the image, there's no ground truth. There's only, what a plurality of people on Amazon Mechanical Turk said. And that becomes the standard for what accuracy means in this particular model. So I think it's really important to remember that in many cases, we do not measure truth, we measure consensus. And that gap can be significant. And as Kate Crawford has pointed out, I know you're going to be hearing from Kate in a couple weeks, so I won't elaborate too much. But some of her work has identified these purely subjective categories in ImageNet. For example, failure, loser, non-starter, unsuccessful person. And, you can go on Amazon Mechanical Turk and get people to click on pictures that look like a loser. But obviously, we don't know anything about these people. They could be perfectly successful, happy, self-actualized people. And so what are we really measuring? What are we really capturing with this category label other than just formalizing human stereotypes? Okay, so there's a question of what is it that we're really measuring, and is the ground truth really the ground truth? There's also, I think, this really important question of what is the prediction actually going to be used for? And so you get this often with COMPAS in particular. It makes these 3 different risk predictions: violent recidivism, general recidivism, and failure to appear in court. These are in practice often conflated. And in fact, many other models don't even take the trouble to distinguish these different predictions altogether, when in fact, these predictions are quite distinct. Someone who's going to commit a violent crime is potentially a very different category of risk than someone who's just going to not appear. COMPAS also distinguishes between what they call the risk predictions and what they call the need predictions. And need predictions are things like this person has a chemical dependency, or this person doesn't have stable housing, or they don't have a robust network of support community. And those predictions are meant to indicate that we should give additional services to the person and help them. And that's why they're coded in green. But in practice, oftentimes these are just treated as one more category of risk, and all the more reason to lock someone up. And I think, one of the other ironies with COMPAS in particular is that it's explicitly designed to be used for pretrial detention, not for sentencing, but it has been used in sentencing anyway. And so I think, we're maybe at a point with the field of ML where we need something akin to the warning label on the side of a prescription that says, use only as directed. But this question of what are we really using our prediction for, I think has a number of really kind of deep implications. So the city of Chicago had put together in 2013 what they call the strategic subjects list, informally a heat list of people who were at a higher risk than normal of being victims of homicide. And it turned out this prediction was calibrated, it was accurate. The people on this list were 223 times as likely as a regular Chicagoan to be the victim of homicide. And yet, homicide is so rare that only 0.7% of the people on that list were victimized, and the other 99.3% were not. And so there was an analysis of this policy by Jessica Saunders at Rand Corporation, just kind of making the point that what good is a prediction, even an accurate one, if it's totally unclear what intervention you would actually propose to make on this population to try to help the 0.7% of them that are going to be potentially victimized. What do? You just tell them to be careful? What do you do? This gap between the prediction and the actual real world intervention was kind of never, to my knowledge, never really resolved. Finally, in the criminal setting, there's this question of what do you do with a prediction that someone is going to fail to appear for their court appointment? Well, one thing you can do, one intervention is to incarcerate that person. The other intervention is to release them and then send them an SMS reminder, 24 hours in advance saying, hey, your court appointment is tomorrow. And Jennifer Ellick and her colleagues at the National Center for State Courts have shown that, in fact, something as simple as a text reminder is incredibly effective. And so, again, this is sort of outside of the actual objective function of the model, but I think a lot of these critical ethical questions are happening essentially between the prediction that the model makes and the real world intervention that prediction is meant to support. And oftentimes we have more options available than it might seem. So thus far, we've been talking mostly about supervised learning. So for the last 10 minutes or so, I want to just turn the focus a little bit to reinforcement learning, because I think some of the questions of alignment there are every bit as significant as they are in supervised learning. So again, I think this audience, I don't have to explain reinforcement learning and the incredible advances that we've seen in the last 10 years in things like Atari, board games, robotics, self-driving cars, et cetera. I think it's less appreciated even in the research community. how quickly reinforcement learning is coming to these consumer-facing applications. So this is, for example, a white paper by Facebook in 2018 talking about switching from a supervised learning model to DQN, reinforcement learning model, for delivering notifications. And I think it's particularly ironic that they use DQN because that's the exact same model DeepMind used to beat all of those Atari games. So at a formal level, Facebook's notification system is literally, playing us like we are an Atari game. But in a reinforcement learning setting, rather than this objective function or this kind of constraint that you would have in a supervised learning scenario, you have this reward function. Your program is, your agent, whatever, is designed to explore this environment and maximize its points or its score. And so how do you actually operationalize that? Well, it turns out even in a video game, it's very hard to operationalize what you want your agent to do. So this comes from OpenAI. They were training a RL agent to play this boat racing game, but it was very hard to operationalize winning the race, because how do you get the model to understand where the track is and where the other boats are, and if it's in the front or the back or what lap it's on, et cetera. So they did what I think a lot of researchers would do. They just used points as a proxy for that. But the agent learned to just do these circles around this little harbor where there was kind of an infinitely replenishing power up that would give it this inexhaustible supply of points. And it completely ignored the race and didn't do what it was supposed to do. And again, this is within a video game. So in any sort of more real world setting, it's incredibly, incredibly difficult to actually create a reward function that incentivizes the behavior that you want to see. Now, I think anyone who's worked in RL has their own personal stash of ways that this can go wrong. One of my favorites comes from a group of Dutch researchers in the 90s, training an RL agent to pilot a virtual bicycle towards a destination. And so they were doing this reward shaping, and they gave it this little incentive for making forward progress toward the goal, but they forgot to subtract points for progress away from the goal. And so their agent optimized to just go in circles really, really, really fast. Similar thing happened to David Andre and Astra Teller, who now runs Google X. In his grad student days, they were working on a soccer competition, and they decided to give their RL agent a bit of a shaping reward, pseudo reward for taking possession of the ball, because that's kind of a nice precursor to actually passing and scoring. They thought this was a reasonable way to speed up learning. Unfortunately, there was a loophole yet again, and their robot learned to approach the ball and just within range, vibrate its paddle as quickly as possible to repeatedly take possession of the ball and accumulate an infinite string of those pseudo rewards. So the alignment problem in an RL context, I think, rears its head very directly of how do we create a reward function that actually incentivizes the behavior that we want from this agent. Now, many people are arguing that it is essentially too unsafe to ever do this directly, to ever explicitly specify the reward function ourselves, that we can never completely predict all the loopholes that our agent is going to find. And so we need to treat the construction of the reward function itself as a machine learning problem, something to be learned from data. And I'm bringing this up. There are very deep roots here in cognitive science. For example, the work of Felix Varnikin and Michael Tomasello, showing that, for example, if you bang a stack of magazines into a cabinet, suggesting that you're trying to put them away, but the cabinet's closed, children as young as 18 months will kind of stumble over, open the doors for you, and then look at you expectantly saying, is that what you wanted me to do? I think this is really remarkable. Partly, I want to emphasize that this is like 2 years before they have theory of mind. So years before children can understand that you perceive the world differently than they do, have different beliefs, different perceptions. They understand that you have desires, and they can infer what your desires are based on the way that you're behaving. So people, obviously in computer science, we know this basic idea as inverse reinforcement learning, where the system observes your behavior and tries to infer essentially what points are you trying to obtain, and to build a policy to achieve those same points. So this is something that's been used in kind of toy problems initially and increasingly in real world settings. So the Stanford helicopter that could learn to do all these tricks based on your attempted tricks. So even if you couldn't do the trick perfectly, or even if you couldn't do it successfully, it could use IRL to figure out what you were trying to do and then construct a policy that could achieve that goal better than you yourself could. So this idea that our systems should infer what our goals are just by, looking at our behavior, asking us questions, I think this has implications going all the way back to the kind of supervised learning setting, things like, misclassification in image tasks. And Stuart Russell, for example, has pointed out that, we should probably be skeptical of the cross entropy loss that we use to train image classifiers, which kind of implicitly assigns if you think about it as like a loss matrix, we implicitly assign an identical loss for miscategorizing any X as any Y, as long as Y is not equal to X. And that's maybe not really what our, the real human reward function here, right? So we know that some of these miscategorizations could be, a millionfold more harmful or disastrous than others. And so what would it look like to actually treat this loss matrix itself as part of the machine learning problem? Same thing is happening in robotics. We're seeing the work of this whole new generation of roboticists, including Chelsea Finn, who's at Stanford, kind of extending this to really high dimensional settings. For example, putting plates in a dish rack, and the robot observes you doing this by manipulating it and can finish the task for you. For me, I think the one of the most encouraging papers that I've seen in this space comes from Paul Cristiano at OpenAI and Jan Like at DeepMind. And they were asking the question of, okay, we have IRL that you can do by providing demonstrations, but not everything that you want you can demonstrate. And not everything you want you can sort of perform on the robot body itself. But there are many things in life, that we want, and we'd identify them if we saw them. We could recognize them. And so they came up with this idea where they'll have this virtual robot in a Mujoko environment that's trying to build a model of what it thinks you want based on showing you pairs of video clips of its behavior and asking you which of these two behaviors is closer to the thing you want me to do. And in particular, they wanted to see if they could get this Mujoko robot to do a backflip. So it starts off just writhing around at random, and you see these two clips, and you have to pick which one looks slightly more like a backflip. And it's building this reward model based on your preferences, as well, simultaneously with trying to optimize a policy to maximize that reward. And after 900 comparisons, so that 900 bits of information, which is not very much at all, the robot can optimize for this. It's probably coming through a little bit choppy over the network, but actually quite fluid, beautiful backflip, tucking the leg to kind of increase its rotational speed, sticking the landing. And I think this is, for me, one of the most hopeful results that I've seen in a long time. And it suggests that, even in these cases where we can't build a reward function ourselves to explicitly contain all the things that we want, we can't even demonstrate it. All we know is that we'd know it if we saw it. Even in these situations, we can still impart some notion of human normativity, human values into the system. Obviously, I think there's a very long way to go. I think the dangers and concerns that people have in this area are totally real. But to me, I feel very hopeful and in fact, exhilarated when I think about this. I think we really are rising to the occasion, meeting the moment, so to speak. I think we're seeing the birth of a new field and the start of something big. And I think it has as much to teach us about these fundamental scientific questions as it does to teach us about ourselves. So I want to close with, my mind keeps going back to this radio conversation that Alan Turing took part in on the BBC in 1952. And he's talking about these really early experiments in machine learning. He says when a child is being taught, his parents are always intervening to stop him from doing this or encourage him to do that. And it won't be any different when we're trying to teach machines. I've been doing some experiments, he says, in teaching a machine to do these basic things. And a great deal of these sorts of interventions are needed. And his co-panelist, Jeffrey Jefferson, interrupts him and says, "But who is learning, Turing? You or the machine?" And Turing replies, "Well, I suppose we both were." Thank you so much. I look forward to your questions.
Thank you very much, Brian. That was a great talk, and I also appreciate how you managed to plug several other talks in our series over the course of your talk. If viewers out there weren't following the chat, I put in the registration for Tim McHebrew's talk, February 22nd, and Kate Crawford's talk on March 8th. So I'll just start off with a question of my own, which is sort of related to Timnit's recent situation with Google, which is where are the incentives going to come from for tech companies that use these models to make sure they're incorporating these solutions that I think mostly the academic community is coming up with to minimize bias, to minimize erroneous results. It doesn't seem like regulation is happening anytime soon. It almost feels like PR is maybe the biggest incentive at this point, and I'm not sure that's strong enough, but what do you think, and what did you hear from talking to experts on this topic?
Yeah, I mean, I think her departure from Google raises a lot of questions in this area, as it should. I think for me, it's a reminder that I go back to the etymology of the alignment problem itself. So the alignment problem, the fact that we're using the word alignment, it's essentially the computer science community borrowing this term that had existed since the 80s in the economics literature for talking about, like, how do you align the values within an organization? How do you align the incentives between a manager and their subordinates, or between two parties in a contract? And for me, I think it's a reminder, perhaps a sobering one, that the alignment problem as such was always a human problem first. And I think it's going to be a human problem in the end as well. Even if we can solve the technical dimension of how do we make sure that, a group of people creating a ML system, the ML system is aligned with their intentions and their values. Solving that is an enormous technological scientific feat, and it's not clear if it is soluble, but let's just assume it is. But that's just one link in the chain, right? We're just talking about the creators of the system and the model. But that's part of this huge chain of they have to respond to the incentives of their managers and their executives and their board and their shareholders. The system impacts people who are stakeholders that are not actually part of the deliberative process of building the model. And so it's an alignment problem all the way up and all the way down. And so for me, the sobering thing, the giddy optimism that I feel about the technical side of the problem, I have to say that I don't share that feeling when I think about the human governance and the human sort of institutional design questions. Is it going to come from regulatory pressure? Is it going to come from competitive pressure in the market? So far, I think we've seen something kind of remarkable, which is that machine learning expertise is so valuable that the people who have that expertise have, I think, somewhat unique bargaining leverage in terms of what company they work for. And so we're seeing people using that to advocate for greater open source work or greater contribution from industry back to kind of the public or through academic conference papers, et cetera. So maybe actually the employees themselves willing to walk away if the company doesn't align with their values. I think that's maybe a really powerful part of the puzzle as well. But I think I don't know. I think it's, for me, one of the more intractable parts of the problem. And I think it's probably going to take a little bit of everything.
Great, thank you. We have a couple questions from the chat. We may not have time to get to all of them, but continue pasting questions in in either YouTube or Zoom. So we have a question from Dhruv, which says, based on current models and processes like quantum computing, when is it likely that a fully functional AGI would be ready for deployment? So I guess, did you touch upon quantum computing in the book, and where do you see an intersection there potentially?
Yeah, I don't get into quantum computing in the book. And I haven't been following that space closely. So to some degree, I think your conjecture is as good as mine. I think in terms of AGI, I have this feeling I'm sort of a slow takeoff person. I think there are sort of three camps of people. There are people that are saying it'll basically never happen, or it'll be centuries. There are people that are saying it's going to happen overnight one day, and we're going to be screwed in a very sudden, blindsided kind of way. And then there are the people who think, it's definitely happening. We're probably on the road as we speak, and we're going to be boiling the frog essentially 1 degree at a time. That's the camp that I put myself in. There's no fundamental reason we're not going to develop AGI. I think a lot of things that we already have AGI-esque aspects. I certainly think that GPT-3, for example, you could make the case that GPT-3 or the OpenAI API goes into the history books as the first commercial AGI product. Now, from the several decades from now, we'll say that it really sucked because it can't do X, Y, and Z. But I think it was, from a business model perspective, it was the first AGI product. It was this completely flexible thing that you could give whatever prompt you want and use for sort of whatever purpose you want. So I think we're on that road. And I think we're going to keep moving the goalposts. And so it's going to be pretty hard to say when it comes. But I think, the number of fundamental breakthroughs required is, in my opinion, somewhere between 0 and 2.
Great. So we're coming up at the end of the hour here, so I'm going to go ahead and turn it over to Nick for today's outro.
Thanks, Rob, and thanks, Brian. Really interesting overview. Lots of interesting stories, I think, in this area. I think really telling, that sometimes people don't fully appreciate the consequences of what they're building or deploying before they actually deploy it or test it out. I think we could have a whole nother discussion about testing and ethics and, how you actually make sure that what you're about to unleash is aligned. But maybe that's for another time. I look forward to reading your book. I think Rob put in the chat, there's a link where you can sign up for a copy. I signed up for one. I hope you send me a copy. Cool stuff. Thank you. I wanted to remind folks that next week we have Andrea Parker, who's a professor at Georgia Tech, works in health informatics. And so we'll be hearing from Andrea next week, Tuesday. It's a special time, Tuesday at 11 Central. And so please join us then. And then following on that, we have some of the talks that Brian so kindly foreshadowed for us. So thanks, Brian. Hopefully, if people sign up for books, hopefully they'll have a chance to read your book before those speakers come, and then we can ask them hard questions too. Great. So thanks, everybody. And then I think I just want to close by reminding folks that there are a number of ways to interact with CDAC, even in these remote times. You can find us online, Twitter, LinkedIn, YouTube, GitHub, and also just want to keep people apprised and reminded that Summer Lab is coming up. That's for high school students, undergrads looking for research mentorship opportunities with faculty at UC Chicago in the area of data science. Applications are due at the end of the month for that. Our postdoc program, the application window has closed, and I'm excited to report that we had a lot of enthusiastic reply to that, and we look forward. We're in the process of reviewing those now, and we'll hopefully have a fantastic, exciting new cohort of postdocs come fall. And then finally, I think especially for cybersecurity professionals who may be listening, I wanted to apprise folks that CDAC is offering a professional ed course in machine learning for cybersecurity that is due to launch just about a month. So keep your eyes open for that, and there's some more information at the URL here. So thanks very much. Thanks everyone for attending. Thank you, Brian, for a fantastic talk. And we look forward to reading your book. Those of us who haven't had a chance to read it yet, I think we're really looking forward to it.